Okay, so in addition to the seafloor preserving the magnetic field that was present when the rock cooled, it also contains minerals that are amenable to dating, to using radiometric dating techniques to assign absolute ages to the formation of those rocks. And the figure in the bottom right shows the distribution of those ages. You see the youngest material is present at the ridge axis, and it gets progressively older as you move away. And in general, as it gets older, it cools. And as it cools, it becomes more dense. And so we talked a lot about how it requires achieving a certain density before it can kind of break free of a continent from a passive margin and turn into an active subduction zone. It doesn't necessarily have to be young to be subducted, right? We have the subduction of the actual mid-ocean ridge itself, so subduction of actively generating rocks, basically age zero, were subducted beneath the North American continent. And you can see that the remnants of that, or the current situation on the slide, right through here. The mid-ocean ridge comes out, goes through California basically, and then comes out of the Gulf of California and down the East Pacific, right? So they don't have to be old and cold to be subducted if there's an active subduction zone already. But for these passive margins over here off the coast of Africa and North America to become active subduction zones, what's really required is that this rock get old enough that it gets dense enough that it activates subduction, which just kind of breaks away from the continent. This low density continental crust made up of felsic minerals and felsic rocks, which are low density and cannot be efficiently subducted, breaks free and starts being recycled into the Earth's interior, back into the mantle. And when it does, obviously it leads to a variety of things, which we discussed. But those relationships are important, okay? And so we talked about the age of the ocean crust and how that also supports this notion of plate tectonics and seafloor spreading. And then we talked about the plate boundaries themselves, right? And so we talked about convergent and divergent plate boundaries, those where plates are moving away from one another or towards one another. And you can see those on the iPad. There are subduction zones and there are mid-ocean ridges. New crust is produced at mid-ocean ridges or divergent plate boundaries, and crust is consumed or destroyed in convergent boundaries, where two plates come together. Either turns into a subduction zone or into a continent-continent collision and massive amounts of uplift. Okay, and so at this point, we have kind of built the idea of the Earth system. We have a lot of concepts under our belt here. It's a ton of information, but it all works together to produce the surface conditions that we see. We could even throw them back on here, right? Let's see, where are circulation cells there? Our general wind patterns. You can't really see those very well, but you could. I think I do, right? I have this, right? This is kind of a reflection of the vegetation cover, right? The presence of deserts around 30 degrees north and south. I think there's only one continent in that area, but there's some ice sheets up on the northern north and south poles. Anyway, we've built up a pretty holistic view of the Earth as a system so far. There's a lot more we're going to explore, but we're off to a good start, I think, given this foundation. We went from here into talking about the plate boundaries specifically, and so I'll do another real short video, although it might be like 6 or 8 minutes, honestly, to get through all the kind of points we touched on. But at this point, I think it's nice to kind of pause and look at the Earth as a whole, from this perspective.